Welcome to Robotics 1. We are studying chapter 8, which is on the motion control system. And in today's lesson, we are going to talk about a very important concept, which is known as transfer function. So what is this transfer function? You can think of transfer function as a black box wherein you have some input, and what this transfer function does, it takes this input and gives you an output. So this is the transfer function and this is an output. So by definition, the transfer function is defined as the Laplace transform. So transfer function is nothing but the Laplace transform of output divided by the Laplace transform of input. And this is a very important definition. Once again, let me repeat. Transfer function is nothing but the ratio of Laplace transform of output divided by the Laplace transform of input. In last class, we spent significant amount of time discussing what the Laplace transforms are, how to find Laplace transform, and then we compared the response of the Laplace transform to solve ordinary differential equation. So few key things about the transfer function. Transfer function is, in this class, we are going to study for linear time invariant system. And Laplace transform is used in system analysis. Laplace transform is used for linear control theory analysis to understand the stability of the system and so on. But one thing I just want to clarify before we proceed further is, in the last class, we talked about the concept of eigenvalues. So you have a real axis and you have an imaginary axis. And here, all the values are positive. Here, the values are negative. If the system eigenvalues are on imaginary axis, purely imaginary axis, if the system eigenvalues are on the imaginary axis, the system is simply stable. And I will come back to this in just a minute when we looked at the Laplace transform, transfer functions, and so on. If the eigenvalues are in the left half plane, the system is asymptotically stable. And if the eigenvalues are on the right half plane, the system is unstable. Now, what it means is, if you want to make system stable, you have to cross this imaginary axis. So this axis, which is the imaginary axis, is super important. If you are on the imaginary axis, if the eigenvalues are on the imaginary axis, the system is simply stable, which means your system response is going to look like sinusoidal, not growing, not decaying, just staying within bounds. If the eigenvalues are here, then you will see that the system response decays down. And if the eigenvalues are here, then you will see that the system response kind of grows. And remember this, because when we talk about the Laplace transform, when we talk about the transfer function, the same concept is applicable when we study stability. So what I want to do is, at this point, I want to take a very simple example and then see how do we find out the transfer function. So let me write the system in the time domain. So this is the same system that we talked about, the second order system that has spring, mass, and damper. So this is the mass, M, spring constant K, damping constant C. And what I want to do is I want to have an external excitation, which is, it's typically called U of t or F of t. So I'm going to call this U of t. And the system response is the displacement, which is I'm going to call X of t. So U of t is nothing but input, and X of t is output. Now, the reason I'm saying this is input, because if you think about the system, initially the system is at rest. If you start applying U of t, maybe it's a sinusoidal force, then the system would start oscillating back and forth. In other words, X would be sinusoidal. And clearly the amplitude of that sinusoid and the actual frequency of that sinusoid is dependent on the values of spring and damper. Now what I want to do is I want to write the differential equation of motion. So at this point, just take a minute and try to write the differential equation of motion by yourself. If you recollect, the differential equation of motion is going to be mx double dot plus cx dot plus kx is equal to u of t. This is the differential equation of motion in the time domain. Once again, let's identify the input and the output. So this is output and this is input. Now what I'm going to do is I'm going to find out the transfer function. By the definition of transfer function, it is the Laplace transform of output divided by input. So what I'm going to do is I'm going to take this system and I will rewrite it over here. Mx double dot plus Cx dot plus Kx is equal to U of t. Please note this is in the time domain. And why this is in the time domain? Because the independent variable, so independent variable is time. This is very important. Now what I want to do is I want to take the Laplace transform of the left hand side and the right hand side. So let's start with what we did in last class. If you have x of t in time domain, in Laplace domain, you're going to have x of s. If you have u of t in time domain, in Laplace domain, you're going to have capital U of s. If you have x dot of t in time domain, you're going to have s multiplied by x of s in Laplace domain. X double dot of t is going to be s square multiplied by x of s in Laplace domain. So you have the time domain and then you have the Laplace domain. Now I'm going to substitute these transformations in this equation. So this equation becomes ms square x of s plus cs x of s plus k x of s is equal to u of s. Now I want you to look at the transformation that took place. So the derivative disappeared and derivative was replaced by an algebraic equation. And it's very clear, x double dot, which was the time derivative, now become s square x of s, which is nothing but an algebraic relationship. So what I can do now is, which was not possible earlier, and this is super important, I can take x of s common outside. So basically, I can take x of s outside and I have u of s something like this. Now, once again, please note that this is my output and this is my input. So what I want to do is I want to define the transfer function is the Laplace transform of output divided by the Laplace transform of input, and this, as you can see, is nothing but 1 divided by ms square plus cs plus k. So this is nothing but the transfer function of the spring mass damper system. Now, this transfer function has some interesting properties, and I want you to understand what this means. This transfer function, and when you see MATLAB or when you write, when you consider a block diagram, this is considered as a block diagram. It is written as ms square plus cs plus k. And now what I can do is, if I want to study the system response, I could have u of s entering over here and I would get x of s as an output over here. So you would have input here and you are going to have an output here. Now this input can be anything. So for an example, if I want to study the response of this spring mass damper system, then to maybe a sinusoidal excitation. So my u of s is sort of sinusoid, and I feed that sinusoid to this transfer function, I would get the response of the system x of s. Now there is something that needs to be said here, and I have to be super duper careful. Typically, when you have input, it is defined as u of t. Say for an example, it could be a sine omega t, or it could be just t, or it could be a constant, say 2. Now, when we are using transfer function, we need to take the Laplace transform of this function, and then feed it. Because please understand, what is happening here, this is nothing but a simple algebraic operation. So this is an algebraic operation. Multiplication is not a differential operation. It's an algebraic operation. So when you have this algebraic operation, so that means u of s is just multiplied with something that you have here. And this multiplication is possible because u of s is in Laplace domain. and this also is in Laplace domain. And then the response that you get is also in Laplace domain. And then what you have to do is you have to take the inverse Laplace to get the response in the time domain, because here there is t. So you have to take inverse Laplace. Now, good news here is all this transformation or all this mathematical analysis can be easily performed using MATLAB. In other words, this you don't really have to uh, go through taking the Laplace transform of input, then converting, multiplying that with the transfer function, and then finding the Laplace transform of output and doing the inverse of the Laplace transform. All this mathematics is handled by MATLAB. And I'll take an example in just a minute to show you how would this problem be typically solved using MATLAB. So, but one thing I want to understand at this point is, tell me one potential case where the denominator of the transfer function could become zero. So the question, let me pose this question slightly differently. Now here is the question. The question is, I have this function. So this function is given as ms square plus cs plus k. I have this function and this is being multiplied by some constant. So let me just say that I'm feeding 1 to this. Now my question to you is there any possible value of s? So at what s the output will be infinity? And I will pose this question again. So the way I pose this problem is, think about transfer function as a block or a mathematical operation, a block or a math operation. And you are supplying or you're multiplying by a constant number 1. But I want to see, or I want to check, is there any particular value of s at which the system response could become infinite? And the answer to that question is, well, we have a quadratic expression. If this expression, and I will rewrite this again just for clarification, if this expression 1 ms square cs plus k, if this becomes something like 1 divided by 0, then my transfer function is going to be infinity. So when I get 1 divided by 0, which is nothing but infinity, and once it is infinity, infinity multiplied by any number will land up with infinity, which means if I could solve this equation, ms square plus cs plus k is equal to 0, and find value of s, find value of s, let's see what happens. This is a quadratic equation. This equation can be solved with the formula minus b plus minus square root of b square minus 4ac. And this equation is minus c plus minus square root of b square minus 4ac divided by 2a. So this is the value of s at which system response is infinity. Now I want to stop here for a minute And if you have your notes from last lesson, I want you to refer to them very quickly and tell me, did we come up with the same expression in our analysis in last class? So I pose this question again, is what I did, I found out a transfer function and I found out the values of S. Please note S is changing. S is changing. This changes. Because please remember, S is an independent variable. So it changes just like time. But now my question is, there is a particular value of S which is given by minus C plus minus square root of C square minus 4mk divided by 2, at which the transfer function becomes singular. And please note, there are two values because there is a positive sign and there is a negative sign. If for some reason m is equal to 1, this equation becomes minus c plus minus square root of c square minus 4k divided by 2. And if you recollect, we have derived the exact same equation in the last class and we called them, I'm looking at the chat window, and we called them, what did we call them? Eigenvalues. Perfect, John. So these are eigenvalues. However, in Laplace domain or in transfer function domain, these are called as poles. So poles, the eigenvalues are used in time domain and poles are used in Laplace domain, but meaning is one and the same. And now I'm going to go back and come up with the same analysis. Check this out. If your poles are on the left hand side, if once again, if your poles are here, then the system is asymptotically stable. If your poles are on the central line here, then the system is simply stable. If poles are on the right hand side, then the system is unstable. So in time domain, you have eigenvalues. In Laplace domain or transfer function, or also called as the frequency domain, you have poles. So please note, eigenvalues and poles, they indicate the same thing. Eigenvalues and poles are responsible for system stability, and it's super duper important. Okay, now at this point, what I want to do is I want to ask if there are any questions. And if there are no questions, please remember eigenvalues and poles. So let me give you a formal definition of poles. Pole are values of S when transfer function becomes infinity. In other words, when the denominator of transfer function, so this is the numerator and this is the denominator. When the denominator of the transfer function is equal to 0 and you get value of S, at that is the pole of the system. So remember, pole of the system is same as the eigenvalues of the system. and you want your poles on the imaginary axis or in the left half plane for the system to be stable or asymptotically stable. Now, at this point, if you have MATLAB, I would like you to go to MATLAB and I will show you an example. How do we work out this problem? And let me, just for the sake of clarification, let me take the example. So M is equal to 1. So I'm gonna take three cases. So let me see. So I'm gonna use MATLAB, and then I will show you how to plot response using transfer function. Now, I would like to take few examples. The first example I'm going to take is I'm going to take value of mass M is equal to 1. Then I'm going to take value of C is equal to 0. And I'm going to take value of damping K, so stiffness, as 1. So this is a simply stable system, which means for this system, the poles are here. The second case that I want to take is M is equal to 1, C is equal to 1, K is equal to 1. So the system is asymptotically stable. So what it means is the poles are in the left-hand side of the plane. And the last case which I want to take is when the mass is equal to 1, C is equal to -1, and K is equal to 1, where the system is unstable. And if you recollect, we worked out the same case in the last class, wherein we looked at a system that had eigenvalues on the imaginary axis, another system where the eigenvalues are on the left-hand side, and the third case when the eigenvalues were on the right-hand side of the imaginary axis. So what I'm going to do is I'm going to work out these three cases, and then just for the beauty of it, and I want to show you how simple it is to study system dynamics with MATLAB Simulink, we are going to use different inputs. So they are different inputs. What do I mean by different inputs? So think about, you have a transfer function. So we will construct this transfer function inside MATLAB. You can construct this in the MATLAB prompt, or you can construct this on Simulink, and I will try to work with both. So what we can do is we can feed sinusoidal function, we can feed a step input, we can feed a ramp input, and then we can actually see how does the response of system look like. So we are going to look at the behavior of this system, and just follow what I'm doing, because what I'm going to do is I'm going to then show you what else is possible when we try to analyze the system response using MATLAB. So what I'm going to do now is I am going to switch my screen to MATLAB. Okay. Now you should be seeing my MATLAB screen. And what I want to do is I want to type Simulink. So hit Simulink, and let Simulink open. It will take some time for Simulink to open. Once the Simulink is opened, I will show you how we can do the analysis. Okay, my Simulink opened, and then I want you to open a blank model. So open a blank model. So now I'm going to switch my screen so that you can see my blank model. So at this point, this is the Simulink canvas you should be seeing. I want you to go to library browser. So click onto library browser. And once you go to library browser, this is what you should be able to see. And in library browser, you can go to continuous, and you will see something called as transfer function. So you should go to continuous, commonly used blocks, continuous, and see transfer function over here. Drag and drop this transfer function block onto your canvas. So drag and drop. Next thing, we are going to need some more things. So go to commonly used blocks and then grab scope. So you see here, scope. This is just to display the response. Then you would see a constant. Drag that constant onto your canvas. And then what I want you to do is I want you to go to sources in the commonly used block. So you see sources, double click on sources, and then here you should be able to see white band. Let me see what other inputs you can have. You have random generator, you have pulse generator, you have signal generator, then you have a sine wave. Drag this sine wave and drop it to the canvas. Then I want you to drag the step and then drag it over here. And the last but not least, I want you to drag the ramp, and then this ramp can be dragged to your canvas. Now I'm going to go back to the canvas, and then you should be able to see the blocks that I have in my canvas. So now if you look at my canvas, I have this constant, I have the sinusoid, I have this ramp, and I have this ramp, and then I have this step. So constant, sinusoid, step, and ramp. So then I have the transfer function block, and I have the display block. So what I'm going to do now is I'm going to input my transfer function for the spring mass damper system. So case 1, numerator coefficient is going to be 1. This denominator coefficient will be of the form m, c, and k. So value of mass, then value of damping, then value of stiffness. And at this point, I just want you to look at the block diagram and the transfer function that we have. The transfer function that we have worked out is something like ms square plus cs plus k. And these denominator coefficients, MATLAB expects the coefficient of s square to go first, coefficient of s to go next, and coefficient of s to the power 0, which is 1, to go over here. So this is the coefficient of s square. This is the coefficient of s to the power 1. This is the coefficient of s to the power 0. And we need to supply their values. So case number 1, mass is equal to 1, damping is equal to 0, and stiffness is equal to 1. And I want you to click OK, and then you will have your transfer function, and this transfer function should look like s square plus 1. Any questions at this point? Now, what I want you to do is so this is the scope. This is the output. Now, what I'm going to do is I am going to join this to the transfer function. And basically, you can just drag an arrow and connect this block. So this block gets connected. Now I'm going to start with some sort of input. So first, let me start with a simple constant input. So I'm going to supply constant input. And here, what I want you to do is, once these connections are made, click run, and then double click on the scope, and that will give you the system response. So observe, hit run, and you will see that the Simulink will save this block, generate the hex file, and then actually run the code. And then you double click on the scope, and you should be able to see. I'm going to switch my screen. You should be able to see the sinusoidal graph the way I have got. Any questions here? Were you able to get the same plot? So I just want to tell you what has happened. So we had a constant input 1. This constant input was in time domain. But as soon as I converted this constant input to the transfer function, which is in Laplace domain in MATLAB. MATLAB found the Laplace transform of 1, multiplied that by the transfer function, and got the result as an output. However, if you look at the scope, what has happened, and it's very important, please note on x-axis you have time. So this is the response of the system in the time domain. So what MATLAB did, it found the inverse Laplace transform and then gave us the response in the time domain. So on y-axis, you have displacement. On x-axis, you have time. Any questions here? If you have questions, you are welcome to raise your hand, or you are welcome to give me feedback or ask me questions in the chat window. Next thing, what I'm going to do is I'm going to attach the sinusoidal signal. So what I'm going to do is, check this out. I am going to go back to my canvas. I'm going to go back to my canvas. You should be seeing my canvas. Take this connection out and then attach this to the sinusoid. So rather than supplying it with a constant input, I'm going to supply that with a sinusoidal input. It's a sine wave. Double click on the sine wave. When you double click on the sine wave, the block parameter should open. Okay, let me see the messages. Yes, that's fine. Depending upon the MATLAB version that you have, you could just have nums over dens. So x was x, yes. In the plot on x-axis, you have time. And please note, if you see that there is a capital T over there, T is equal to 10. That is the simulation time. And on y-axis, you have the displacement of the mass. Okay, going back to the sinusoid. Now this is super important. So sinusoid is given as amplitude multiplied by sine frequency. This frequency has to be in radians per second. Please note, this frequency has to be in radians per second plus phase. And why is this phase important? Say for an example, if you want to convert a sine wave into a cosine wave, so you would just add pi by 2 or 90 degrees to phase plus bias. Bias is the positive shift in the baseline. So if its bias is nothing but the DC bias or the constant value that is added to the sinusoid. So what I want to do now is I will keep the amplitude as 1. I will keep bias 0, but I'm going to change my frequency to 0.5. I'm going to click OK. And then I'm going to show you my block. This is what you should be seeing. So now here in this block, once again, hit run. So this is the run, hit run. And once you do that, just one thing, stop time, you can say 50. So here, stop time, which is simulation stop time, 50, and click run. And see what happens. So now, if you go, let me change my screen. So this showed me the response of the system. But as you can see, this system response is sort of jagged. And the reason this system response is jagged is because the simulation step is not too fine. So if you want to make the changes to the simulation time step, what you need to do is go back to your screen, and then you need to see the simulation parameters. So let me see, where are my simulation parameters? Okay, so they come under model setting, model properties. Let me see, callbacks, no, format, no, modeling, subsystems, upstart, model advisor, simulation. So there is supposed to be a simulation time step modeling, wherein what you can do is you can change the simulation's time step. I don't see it here very quickly, but if you go to simulation time step, if you change the time step, and then you would be able to you'll be able to get some refined results from your simulation. So this needs a change in the time step, but you will be able to get a very clean signal, or you will be able to see a very clean sinusoid. Okay, moving on to the next input. Now I would connect this to the ramp. So connect it to the step input that will be supplied to the transfer function. Again, same procedure. You can click run, and then what you can do is double click on the scope, and I will show you how my scope looks like. So this is how the scope is going to look like. And again, this looks a little jagged, but if you refine the time step, then you should be able to change the settings. Okay, and I will show you how to change those settings. This is a slightly newer version of MATLAB. So I want you to go back here. Now, I want you to look at the right-hand corner where there is Auto ODE. What this means is, to solve this system, it's going to use ODE 485, the MATLAB solver that we used in last class. Now, I want you to left click on this, left click on Auto ODE. Here is the setting. It says View Solver Setting. Click on View Solver Setting. It will take you to the dialog box of the solver. It will take you to the dialog box of the solver. And here, what you want to do is, you want to do fix step, and then it will ask you for solver details solver step size, and you can play with the parameters over here. Say, for an example, you can say this is 0.01 and click OK. And then go back to your screen. And now say run. And when you run, and then your plot should be much, much smoother. So now you can see earlier I had that jagged plot because I used a variable step size, and depending upon the convergence criteria and other parameters, MATLAB chooses the appropriate time step, which may or may not be good from visualization point of view, but I force MATLAB to take a smaller time step. And now, as you can see, my results are much, much cleaner. So to give you one more thing, just go back to your sinusoidal, connect sinusoid to the transfer function and run. And now you will see that your sinusoid is going to look pretty nice. So if once you change the solver step, you should be able to get smooth output from the scope. The last part that is remaining is connecting the block to the ramp. So I trust that you'll be able to do it on your own. So what I have done is I have gone and I have connected my transfer function to the ramp, and then I'm going to run it again. And then once you see the output, you would see this type of ramp. Now clearly, as you can see, this ramp is not a straight ramp. There is slight oscillations because of the poles that we have in the system. So what we have plus minus I as poles. We are on purely imaginary axis. So that's why you would see the ramp output with sinusoid. Now, what I want to do is I want to do something very interesting. And I'm going to disconnect the transfer function. So I will disconnect the transfer function. And I'm going to go back and connect it to sinusoid. I'm going to connect it back to sinusoid. Double click on sinusoid. Double click on sinusoid. And here is what I'm going to change. Amplitude is 1. Amplitude is 1. Bias will stay 0. But this frequency is going to be 1. Frequency is going to be 1. And I'm going to click OK. And once that is done, I go back to my MATLAB Simulink canvas and just change this time to say 5. Change this time to 5. And now run. Now you can see that the system is behaving some sort of in sinusoidal fashion. Let's increase this time to say maybe 20. And then click run. And what I want you to do is I want you to observe the scope. So double click on the scope. So double click on the scope, and then observe how does your scope look like. Can you notice that the system response is growing? And if you don't believe me, go back to your canvas and change your start time to 50. Change your stop time to 50, hit run, and then you will see that you would get a system response that is growing. Now, the question is, why is this system response growing? And I want to give you a very familiar example. Imagine you do your laundry and then you put your clothes in a dryer. So after washing, washer is done, you take your clothes out, put it in the dryer. But when it is in the washer, during its spin cycle, what washer does, the tub starts rotating at different speed. However, if you have noticed, there is a certain speed or certain frequency at which that washer starts vibrating violently. In other words, that washer starts vibrating heavily. And that is something similar to what you see in the scope. So when the external frequency, this is super important, when the external frequency is equal to the natural frequency of the system, in this case plus minus 1i, the system response grows, and this is called as resonance. At resonance, what happens is there is an energy interaction between the external excitation, and the energy gets pumped into the system response, and the system response grows. So that you probably have observed in your washer when it's going through the spin cycle. However, washer doesn't walk away. I mean, washer vibrates violently, but it doesn't break apart because that washer has some amount of damping that limits the system response. So now what I want to do is I want to go back to my canvas. I'm going to go back to my canvas and I am going to make one change. Go back to the transfer function and I'm going to add some damping. So this is 1. So now I have some damping to my transfer function. The first number is the value of the mass. Second number is the value of the damping. And the third number is the value of the stiffness. So click OK. And now you should be able to see the transfer function s square plus s plus 1. Do the same thing, hit run. And now you would notice that since we added some damping to the system, look at your scope block. Your scope block will show you bounded response. So when you look at the scope block, it should show you the bounded response. Remember, we did not change anything. Only thing, our previous system was undamped. There was no damping. The system response was becoming infinite. It was growing. But as soon as we added damping, the system response became stable. It became bounded. Now what I'm going to do is I'm going to detach my transfer function from the sine input and attach that to a constant. So I will attach the transfer function to constant and run. And now you would see this is the response of the system. And this response, there are a lot of things going on in this response. And first and foremost, I just want to make sure that you have all got the same response. So did everyone get, when you apply the input, 1. You got this response? I'm looking at the chat window. Okay. Now what I'm going to do is I'm going to make this screen little bigger because I want to talk about a lot of things in this response. First and foremost, please note the 1. This is 1. So as time goes beyond 10, 15, 20, 25, 30, 35, 40, the system output is equal to input. So our input is 1. So when time is after say 10 seconds, the system output became equal to system input. Have you observed that? What I'm trying to say is after certain time, or as time went to infinity, the system response went to 1. This is called as the steady state response. Response of the system when time goes to infinity is called as the steady state response. Now, so this is an important concept, and I will talk about the definitions in next class, but I want you to observe the steady state response means at time goes to infinity, what is the response of the system? One thing I want you to observe that the system actually went all the way up to 1.18. So as you can see, the system went to 1.18. This is called as the overshoot of the system. So system kind of overshot. It went beyond 1. And so even though our input was 1, the system went outside or beyond 1. This is called as overshoot. But then what happened after the overshoot? The system kind of came back, sort of oscillated back and forth, and then steadied down. So system overshot, came down, and then kind of became steady. Now, please note the final response of the system or the steady state response is 1. System started with 0. So the amount of time the system took to get to 2/3 of its steady state response, and this is the point, 2/3 of the steady state response is called as the time constant of the system. So time constant of the system is how fast or how slow the system is able to respond. Now I want you to understand this very carefully. We started from 0, it overshot, but if you look at the 66.6%, so that point is somewhere over here, and if you drop a vertical line, and I'm gonna try to use my scale here. So as you can see, you click on the scale, and then you can actually you can have the cursor measurements, and you can have your cursor. Move that cursor. Please move that cursor. Go down, go down, go down, go down, and then go to 66.6, and which I'm gonna say 66.6, little bit ahead, and then you would see uh, the time. You can measure the time that is over here, and it will tell you that this time is somewhere. About 0.15. So it's actually 1.65. So 1.65. So the time constant of this system is 1.65. When the system response is 66.6%, and I need to be super careful. Yes, this is 66 point, close to 66.6%. My time constant is 1.6. Everyone understood the concept of time constant? I'm looking at the chat window. So time constant is the time when the system reaches 66.6% of its steady state response. Then the next question is something called as the rise time. Now the rise time is when the system has gone to 90% of its final response. So I'm going to go back and I'm going to set so that this is actually cursor is at 90%. And then you can see the rise time for this system is 2.13 seconds. So this is the rise time for this. The next question is, I want to find out what is the percentage overshoot. So, and again, I can actually, there are a lot of, let's do a simple cursor measurement. So what I want to do is I want to find out the percentage overshoot. So I'm going to go all the way up to over here. And you would notice that this is sort of the maximum value, and that value is 1.16. So you can see the value is 1.16, and that is called as percent overshoot. So the system output is 1, but in this case, system has overshot by 16%. System has gone to 1.16. So the overshoot of this system is 16%. And then if you want to find out the steady state response, you can actually go here and then you will see that the steady state response at time t is equal to infinity is 1. And these are some of the important parameters that we will be studying when we talk about the time domain specifications. So this is an important word. So I'm going to type this in the chat window. So time domain specifications are time constant, rise time, percentage overshoot, steady state response. Then there is something called a steady state error. And these terminologies will be defined rigorously in next class. But I just want to show you what is the steady state error. What is the response at the steady state? Response at the steady state is 1. What is the forcing function magnitude, which is 1? So the steady state error in this case is actually 0. So this is actually called as the time domain specification. Now, once again, real quick, let's look at the time constant. I'm gonna quickly say that my time constant is approximately about 1.6. Now what I'm gonna do is I'm gonna go back to my system, and I'm gonna go to the system, and I'm gonna change my value of the damping. So I'm gonna change my damping value from 0.5 to 10. So what I did, I increased the damping. Click OK, hit run, and see what happens. And you will notice as soon as you hit run, wow, system response does not look like what it was earlier. So system kind of starts at 0, but it doesn't go to 1 even though the time is 50 seconds. System doesn't go to 1 even though the time is 50 seconds. So what I'm going to do is, at this point, I'm again going to go back and see where did we get 66.6% of the response. So I'm going to try to locate where I am on the 66.6%. So this is about 66, about 66. 66. And you would realize that now the time constant has become 11 seconds. So initially my time constant was 1.6 seconds. Now it became 11 seconds. So the system has become super sluggish. So if I added damping, the system has become lazy, system has become sluggish. Next thing what I want to do is I want you to experiment with this. Change the value of damping and you will see that the response characteristic changes. One thing real quick I want to show you is go back and now change this damping to negative number. So if you go back, this is the last case which I want to discuss. Go back to your transfer function block, double click on transfer function, and your damping value, which was 1, change that to -1. And now hit run. And so once you hit run, so let me see just a second here. So denominator coefficients are 1, -1, 1. Okay. And then say you hit run, and then you will see something weird happening. Double click on the scope. Okay, so what you want to do is I'm just going to connect this to a sinusoid. And then I'm going to run. Double click. And then you will notice that your system response has become unstable. And the reason for that is because now you have a negative damping. In other words, your poles are on the right hand side of the plane. And then because of that, the system response has become unstable. So double click on it, click run, and then hit on the scope. And then you will see that your system response will show unstable behavior. And with this, I'm gonna stop here today. And if you have any questions, I would be happy to answer. And if not, I wish you all a very happy Thanksgiving and no class on Thursday. And I will see you next Tuesday. I'm going to stop recording and answer any questions that you may have.